Let me show you how to be a good Bayesian.
My guests today are Adrian Seyboldt and Eliot Carlson. I'm sure you know Adrian by now, but this time he's brought Eliot with him, a research analyst in Bob Carpenter's group at the Flatiron Institute who spent the last year co-writing a paper with Adrian. That paper is about preconditioning, the process of transforming your target distribution into something Hamiltonian Monte Carlo can sample efficiently. The catch is a chicken and egg problem, since preconditioning requires knowing things about your posterior that sampling is supposed to reveal in the first place. Adrian and Eliot's fix is to use a piece of information samplers already compute, but mostly throw away, the gradients of the log density, and to formalize the whole problem using something called Fisher divergence. We get into mass matrix adaptation, why Stan and PyMC's default approach leaves information on the table, when to reach for diagonal versus low rank versus normalizing flow adaptations, and a benchmark results that's hard to ignore. A median 4 times speed up across 114 models. This is Learning Bayesian Statistics, episode 163, recorded June 12, 2026.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all.
Eliot Carlson, welcome to Learning Bayesian Statistics.
Thanks for having me.
I'm very happy to have you on. And obviously, Adrian Seyboldt, willkommen nach Learning Bayesian Statistics.
Great to be here.
Yeah, always great to have you back, Adrian. You're basically a co-host now, so you know you're at home. Feel free to interrupt me whenever you need, and say whatever you want, But today, we're gonna talk about what you guys have been working on, because you've been working together. I think also with Bob Carpenter on that project, and so we're gonna talk about a lot of algorithm, Nutpie, Rust, things like that today. It's going to be a fun episode. But to start with, of course, Eliot, it's your first time on the show, so we need your origin story. Okay, what are you doing nowadays, and how did you end up doing that?
Okay, well, I'm currently a research analyst in Bob Carpenter's group at the Flatiron, and also I've been for the past year working with PyMC Labs, to whom I was introduced via Adrian. So I did an undergrad in stats and a master's in stats, and I think I arrived at Bayesian stats the reverse way that most people do, where, to MCMC in the reverse way. So I first learned about MCMC without really knowing much about Bayesian stats, and was interested in that. And so I was introduced to Bob and asked if I could, if he had a project, an MCMC related project for me to work on. And then he introduced me to Adrian. He said, I have an algorithm I've been trying to understand for a year now, but I haven't had the time to fully dive into it. So then that initiated maybe a year-long process of us writing this paper, which was a lot of fun and learned a ton.
This Adrian guy just never wrote down his algorithm in a proper way, right?
I mean, I understand you, Adrian. Like, writing papers is not the funniest part, I would say, of the job. It's not the one I enjoy most. So, I think it's much more fun when you do it with other interesting.
Actually, writing it with Bob and Elliot helped so much. That was a lot of fun.
Yeah.
So
yeah, exactly. Writing alone is just, oh my god, yeah, I hate that too. So Elliot, actually, so you answered that a bit, but I'm really curious also to what drew you to Bayesian inference specifically, because I think here you told us how you ended up working on HMC basically and on samplers. Were you introduced to Bayesian stats before that, or did you discover them also just with this sampling work?
Yeah, so I think the chronology was I was first taking a class in stochastic processes and Markov chains, and then I learned about Metropolis Hastings, and I thought, oh wow, I don't know why, I just thought, wow, this is really cool. Even though I didn't really know what it was used for at all, which is kind of what I meant in like reverse way, because I think most people view sampling as like this ugly thing they have to do when they want their models to fit. But anyway, so once in the past couple of years, now that I've been exposed to more, of the Bayesian methodology, I had become more interested in that in and of itself, I think. Especially just seeing how powerful it is for, especially like researchers in scientific domains who have prior information from other experiments and things like, Adrian and I have worked on a project where this has come up a lot, where, yeah, people have priors or, from other experiments that they need to integrate into their models. But I would say that Adrian may be the same. The fun comes in the sampling part.
Yeah, I think Adrian will relate to that. And well, actually, Adrian, it's your third time on the show, so I will refer to your previous appearances. Episode 74, I think, was your first one, where we talked about your. Well, that was, I think the first time. Yeah, and that was the first time we talked about zero-sum normal, and also about Nutpie and the work you did on that and why you started doing that and why Rust is interesting. So I encourage people to listen to that. Episode 76 also with Bob Carpenter, which is great background. And episode 133, where you joined as a guest star with Sean Pickney, because we talked about all things algorithm efficiency, but also zero-sum normal in Stan, which Sean implemented. So that was a nice crossover episode. So I recommend listeners to listen to these ones. But maybe can you tell us, since then, what changed or what evolved in the project, especially Nutpie, and also what you've been working on lately beyond the paper, of course.
Yeah. So kind of in Nutpie itself, kind of from a high level, I would say things haven't changed that much. So the basic mass matrix adaptation algorithm has stayed the same. There was a little bit of tweaking, like the window sizes are different and they are growing now, things like that. Kind of around that, though, the project has changed quite a bit, I would say. So got a lot more robust. So has a lot more users, so they definitely notice whenever I break something, people actually report it in issues, which is a strange feeling. So you notice that people seem to be using it now. So yeah, just has been a lot more tested, I would say. I guess one bigger new item is that it has an R interface now as well. So not just a Python interface, but an R interface. It's actually not written by me. Somebody else wrote that. I was really happy that appeared. So people can now use it from R as well if you have Stan models or something like that. And I think that's probably the biggest change there. Also, on the mass matrix adaptation side, the low rank version, which has been around for a long, long time, it works now much better. So when I tested that years ago, before writing the paper, it was like, somehow it didn't really work that well. Then when we wrote the paper, I just ran the benchmarks again and suddenly it was working well. I never was able to figure out what really changed. Maybe my benchmarks were just wrong, or I had no idea. I had the idea it should work well, but it somehow didn't for some reason. Now it does. So I'm not sure if that's actually a change in Nutpie or just me looking again. But yeah, that's definitely worth a look if for anybody who's working on models that are not trivial to sample.
Yeah. Actually, we can talk a bit more about that, and I think it's a nice segue into your paper. So can you tell people what even mass matrix adaptation means? I guess it's a complicated word, an intimidating word when you haven't heard about that. So what even is that about? Why would you even care about it for a model?
So there are completely different ways of thinking about the mass matrix. One way is it defines an inner product, and you need an inner product for nuts. That's kind of the math side. If you're a mathematician, that maybe tells you something. Otherwise, maybe that's not too helpful. Kind of, if you have divergences or something, the sampler always tells you, you need to reparameterize. So you need to find new parameters, new way to write your original model. And the way I tend to think about the mass matrix adaptation most is as an automatic reparameterization, in a sense. Just a really, really dumb one that doesn't fix much, but it fixes really, really important things. Namely, kind of the diagonal version of mass matrix adaptation just rescales your variables.
I would also add that, I think sometimes the term mass matrix, it sort of drags you into the physical interpretations of HMC, which are really beautiful if you understand physics, which I do not. So, but really, you can just think of it as what we call preconditioning. So just changing the geometry of your distribution, and you can show that using a specific mass matrix is the same thing as just sampling from a slightly shrunk or stretched distribution, or a distribution with some linear transformation has been done upon that transformation being the mass matrix.
Yeah, thanks, Eliot. I think that's a very intuitive way for people to understand it. And actually, so each time people use PyMC or Stan or other PPL, they are doing that kind of things under the hood, even though they may not know. And that's exactly the beauty of PPLs, right? Is that you don't have to care about that. And so yeah, HMC has that large, if I understood correctly, and you guys reframe me if I'm wrong because you're the expert, but it has this large constant factor that's determined by the curvature of the target density. And so what mass matrix adaptation does, as you said earlier, is preconditioning on that to make sure we're able to sample from the posterior afterwards, after we've tuned. But yeah, how does that work currently in Stan and PyMC, for instance? And what does Nutpie do differently so that we understand a bit more the difference and the value proposition, if you want, of Nutpie? And then we'll dive into your newest paper.
So let's stick with the diagonal mass matrix for a second, so that you can think of, it looks at each parameter and tries to just rescale it. So if it's maybe has a posterior standard deviation of 10 to the minus 4, then it will just scale it up by 10 to the 4 to make it bigger. So that kind of the posterior standard deviation of each parameter as the sampler sees it is identical. And that's exactly what Stan and kind of the default PyMC sampler, what they are doing. They're just saying, I look at the posterior standard deviation and I rescale it such that the posterior standard deviation is 1. And I mean, you could do that manually if you really, really wanted, just introduce new parameters that are rescaled versions of the original ones. You just wouldn't want to. That's not a good use of your time. So we do it in the sampler. So Stan and PyMC, they just use the posterior standard deviation directly. We look at the second source of information. We look at the scores, so the derivatives of the log density. Kind of in an ideal world, you want that the standard deviation of your parameter is 1, but also that the standard deviation of your score, so of those derivatives, that those are also 1. They are both kind of interacting in some sense. And Nutpie just uses the geometric mean of those two standard deviations. And then there's a long discussions kind of how you can kind of say why that is a good idea. That's what we go to in the paper a bit more, and kind of a much more general framework of kind of how to do good preconditioning, and kind of this particular version just pops out of that as a special case. But in this special case, it's just the geometric mean of those two things that we kind of want to rescale in a sensible way. And usually, so there's no guarantee that you can, if you work on it, you can find examples where it's worse. But usually it's better. And usually is, I think, where samplers are concerned, the best you can, pretty much always that's the best what you can do. So yeah.
Eliot, first, maybe you have something to add, or anything you're thinking about on that?
I would say maybe this is jumping ahead, but one basically, a lot of what the paper is doing is formalizing some intuitions and general things that we want out of the sampler. So like one thing I would add is that we basically know that standard normal is HMC will perform really well on a standard normal. And you have this nice fact about standard normals relating the covariance to the covariance of the draws of the distribution to the covariance of its scores. So if you think about, so if you have like a normal distribution is parameterized by a mean and covariance, and so if you look at the distribution of the scores, the gradients of the log density, their covariance is the inverse sigma, the inverse covariance of your normal, which is kind of this cool fact. And so that provides a little bit of intuition as to why. So then when we take the metric mean, we sort of want to combine those two pieces of information. So we look at the inverse scores and the draws.
Okay, yeah. Actually, I think that's a good moment to dive into your paper, which is in the show notes for people who want to dig deeper. Because here, of course, well, we won't make it justice because it's a very thorough and deep paper. So title is Preconditioning Hamiltonian Monte Carlo. I think all of that we just talked about, by minimizing Fisher divergence. So we'll go into that second part just afterwards. But first, can you maybe give us the elevator pitch for the paper and tell us what it does intuitively?
So the big problem that Stan faces, or any HMC sampler, is that when we're preconditioning, basically we want to find some mass matrix that turns our distribution into something that's friendly for HMC to run on. And to do that, you need to know something about your distribution. You want to know maybe its covariance structure or something. But the whole point of doing sampling is that we want to learn about our distribution. So, things like its covariance structure. So that we call that this codependence, the chicken and egg problem, it's known as. So basically, ordinarily, like preconditioning based on draws is how we sort of initially come up with like a very rough sketch of what the distribution might be based on just a few warm-up draws, and then sort of get the motor going. And so that can often take like a huge amount of the sampling time. And so basically so as we said, we have this other piece of information in the form of scores that samplers like Stan are not using. And that can be like really valuable for preconditioning. And since we have them, we might as well try to use them. And so a lot of the work of the paper is formalizing, what information can these scores give us about the distributions, and formalizing like how do we turn this into how do we best make use of this information, I guess.
Yeah. Yeah, I think that's a great explanation. Makes it a bit more intuitive for people. Adrian, do you want to add anything to that?
Yeah, so I guess what I would add is the idea of the general framework of how to do preconditioning. So kind of what the paper really does spend most its time on is a special case of this. So we say we have this objective, how we want to precondition the model, and mostly the appendix kind of have such a very general way written down. And then most of the work is, what does that do in a very special case where we just look at the mass matrix that does linear things. And there we work through kind of what are the influences on the condition number, why does this work better, kind of. But as I said, just in the linear case. And what I really like about this framework is that it's not restricted to that. You can add nonlinear transformations as well. That's kind of where the normalizing flow adaptation that's still experimental in Nutpie, for instance, is coming in. And I think that's where a lot of the interesting research, more researchy side of things look like. Kind of the linear one, I would more say, is more in the engineering part, where, okay, we have the objective, we derive it, we look at derived closed form solutions, we look at the details of that, the closed form solutions, and inspect what it does in that particular simple case. And on the research end, we kind of have this, how can we generalize this? And what does this tell us in general about how to precondition HMC?
Actually, maybe we can talk a bit about the normalizing flow adaptation, because I think it's a pretty intuitive concept, and that will set us up well to then talk a bit more about Fisher divergence and mass matrix adaptation. So, yeah, can you or Eliot give us the idea of why normalizing flow adaptation would be interesting here and what it does? And so you don't need to redefine what normalizing flows are. I have an episode on that with Marilou Gabriel. I'm gonna put it in the related episodes. But yeah, feel free to just give the elevator pitch for it, and then make it in the context, give us in the context of Nutpie and mass matrix adaptation, what it does and why it can be interesting.
I think that especially in applied problems, there are a lot of geometries that are induced by certain parameters that create that basically are not solvable with a linear preconditioner at all. So the most famous example of this is like the funnel, which arises when you have these hierarchical models where there's a variance parameter. So you get this, big thing that's called a funnel. And basically, on either side, any linear preconditioner that you try to apply to sort of tame one side of it, this very thin over here and very wide over here, anything you do to one side will just make the other side worse. So normalizing flows, since they can sort of, since it's a neural network, obviously very not restricted to be linear. And so you can get kind of more sophisticated preconditioners. And yeah, as you mentioned, normalizing flows, you have they're designed in such a way that you have the normalizing, you have the Jacobian, excuse me. And so that can help you. Yeah. So I have not used normalizing flows myself, but I would be interested in trying them out. Yeah.
Yeah. Yeah, I've tried them. I tried the adaptation of normalizing flows, but it wasn't a huge GP model, and in the end, it wasn't giving speed ups for sampling. Actually, the classic mass matrix adaptation was perfectly fine. So it really depends on the models and on the geometry that you get with the posterior, and if it's especially complicated with, funnels, as you were saying, then it's going to help a lot, because what I find super intuitive and interesting with the normalizing flow idea is that basically it just tries with a neural network to learn a transformation of the space that becomes a standard normal. And that really ties to what you were talking about at the beginning of the episode, where, standard normals are super easy to sample in HMC, so why don't we try to do that? And yeah, the idea is that if you have a very complicated posterior geometry, spending more time in tuning and adapting the mass matrix with the normalizing flow can be very interesting, because then it's going to pay off a lot afterwards when you start sampling. Obviously, the caveat is that, well, you have to learn a neural network, so tuning's going to take much more time. But basically, the idea is a bit like to amortize that tuning time with then really fast and efficient sampling. And that's also why pairing that adaptation with normalizing flow with GPUs is going to play extremely well, especially if you are using Nutpie to do that. So yeah, like it's interesting to have in your toolbox for sure, even though you're not going to use that all the time, and really not the majority of the time, actually.
This kind of, I would say, like leads into the Fisher divergence topic. I don't know if you want to talk about that. Basically,
yeah,
like
that's perfect.
The idea of
exactly what I was gonna ask you.
Yeah. So just I'll give like a brief, a simple background, I guess. So most people know about KL divergence. It's basically just divergences being like a way of trying to compare. I'm going to use the word metric. I know they're not like technically metrics, I think, but basically a metric of comparing, how close are two probability distributions to one another. So the KL divergence is the most common one, where you're integrating over the support and comparing the log densities. The Fisher divergence is just slightly different metric, where you're comparing the scores, and you're basically saying, okay, at distribution A and distribution B, when we integrate over those, how close are the scores to one another? And so we can use that as a minimization objective for preconditioning. So how do we get our target distribution? How do we minimize the Fisher divergence between our target distribution and standard normal, which we know works really well? And so that's all that Fisher divergence is, sort of a formalization. And the nice thing about that is that the solution to that minimization problem incorporates both draws and scores, which are exactly the two pieces of information that we have during preconditioning. So it sort of works out really nicely.
Interesting. So what is, two further questions. What is the difference with KL divergence, with most of the listeners will know about, and why is Fisher divergence here a better objective for what we're talking about? And maybe additional question, completely random. Do you know why it's called Fisher divergence, which is like a very difficult, like non-intuitive name?
I actually don't. Adrian, do you know why?
I guess because of Fisher. Kind of, he was doing a lot of work with the score function, so I would assume that's related. It's also closely related to the Fisher information matrix, or Fisher information in general. So I would assume it's coming from that, but I never really checked. It's also really pretty much the same thing as score matching, kind of in different literature. That's it's also called that.
Okay, so. Nice. Well, after that derailing of the thought process because of me, so what is the difference actually with KL divergence?
So the KL divergence really looks at the density, and the Fisher divergence looks at the scores, so the derivative of the density. And it turns out that you can use both, kind of, if you know the full, if you if you have a probability distribution and you know what the derivative looks like everywhere, then you know the full distribution. Similarly to how, if you know the density, you know the full distribution, in a sense. So that those are really complementary. You can use either one or the other one. The reason the Fisher divergence in particular, or there are two reasons the Fisher divergence is particularly useful for us. One is that it just uses the information that we have, which is a nice thing, because we don't really have the density in the first place. We only have the density up to a constant, but we do have the derivative, the score function, directly, because the constant goes away when we take the derivative. So that's nice. The other reason is more related to HMC directly. So HMC really uses the score function to drive you kind of to find the trajectory through the parameter space. So that's really the thing that we want to target in a sense. So we want the trajectory of our sampler to look like the trajectory of a standard normal distribution in a sense. And that's because that's what makes it efficient, the trajectory. It's not so much the density in itself. So for HMC specifically, I think it's the right thing to target. You could actually add additional terms, but that's a different question. So you could look at higher order derivatives as well. I think that's interesting research direction as well.
Yeah, super. Thanks, Adrian. Super clear answer. So, and that ties well with ties up well with the physics interpretation that you were talking about before, Eliot, because the derivatives, like the second order and the kind of the if I remember correctly, if it were that'd be the speed, right? Or that'd be the acceleration. I always mix them up. But yeah, okay, so it's like you're interested in the second order, the change in the derivative, and not necessarily, and not in the density, and not the density itself. And that's what the Fisher divergence tell you. Divergence from what, though? So it's like you look at the density you're trying to sample, the derivative of the density you're trying to sample, and you're comparing it to something to say that it's diverging.
So a divergence is just the math term to kind of like a distance-like thing for different probability distributions. It's not really a distance because it's not symmetric, for instance, but it's like a math term for distance for probability distributions. I'm actually also not entirely sure where that nomenclature, where that name is coming from. But so it's how different is our standard normal to our transformed posterior. That's really what that divergence is measuring there.
Yeah, and also, if I remember correctly, it's like we're talking about divergence and not distance because it can be asymmetric, and it doesn't have to be symmetric. So that's one of the main thing. I think, Eliot, you wanted also to answer my question.
Yes. Wait, which question? Sorry, I forgot.
Divergence to what? And I think what you were saying is that, we are looking at the difference between like the distance, again, in quotes, but the divergence between the target density, the derivative of the target density, and I'm guessing the derivative of a standard normal, I think was your answer.
Yeah. So I think like underneath the hood, maybe it's a little in the weeds, but like at any given point, you sort of want to, you have of your target, you have the point and the score at that point, and then you'd want to say, okay, well, if this were a standard normal, what would the score be at this point? And then we want to change the distributions that those scores match. Yeah.
Okay. Yeah. That's very clear. And now, actually, I'm wondering, in the paper, you present 3 versions of these adaptations, and we've also mentioned a few of them here already. So it's like diagonal, dense, and low rank plus diagonal mass matrix adaptation. So can you walk us through those and when you would reach for each one?
So the diagonal one is just the default. That's kind of the simple one that's really, really fast. So it doesn't really add any overhead. So if you've got a really nice posterior, no correlations or something, the diagonal is the one because kind of that does the work, doesn't spend much time doing anything else. The dense one is really just a math thing that we needed in the paper. So that's not even implemented. You could implement it. There's nothing particularly wrong with it, but I think the low rank plus dense is low rank plus diagonal is really kind of the practical thing that you want if you want to have a way to fix correlations in your posterior. So the dense one is just we need that to derive the equation for the third one. And the third one, the diagonal plus low rank, really is rescale it first with the diagonal mass matrix and then try to fix some correlations that you can find in a way that it scales reasonably well with the dimensions. So kind of if you were to look at the full mass matrix, it would get really, really slow because that's just computationally a lot to do unless you have a very, very, very low dimensional problem. So we use a low rank version of that. It still adds some computational overhead, but it's not crazy, so it scales reasonably well. It does usually add a couple of seconds or so, maybe to the total sampling time, maybe a bit more. So if you're really fast, that you don't want that. If you have a larger problem, it doesn't matter at all. It's like that's a rounding error. And I've actually thought about making the low rank plus the low rank version the default at some point. That's not the case yet, though. But you can think of it, I think, by now as a reasonable thing to do, and not just this crazy. Now I need the big guns thing. Like that's the flow the flow version. That's kind of the crazy one. But the low rank version, I think that's mostly quite workable by now. You might end up in kind of certain situations where something is unstable or so. It might not work, even though the diagonal one works, if something's ill conditioned somewhere. So that can happen, but I don't think it's particularly common.
Okay. And so, yeah, actually, maybe the normalizing flow adaptation would be the fourth one, right? The last one you reach for once you've reached for the three previous ones and they are not working for your case.
Yeah. So the flow version, I'm mostly a bit skeptical of kind of telling people to use it because the implementation is a bit messy right now. So you might get weird error messages. It's slower than it could be. So there's a lot kind of to do on the implementation there. Math-wise, I'm relatively happy with it so far. But just the engineering I think takes a bit more time. Also kind of saying a normalizing flow is doing a lot of work there. Kind of what normalizing flow? There's like a bazillion different ways of doing this precisely, and which one we kind of would want to be the default is like, I don't know how to choose that at this point. So that is a big question, like what particular normalizing flow? And we have one that's going to change for sure. So if you have a model that works now, I can not guarantee that it will also work in a future version. If we happen to change the normalizing flow, for instance, then that will definitely break some things that worked before and probably, hopefully, fix more things that, yeah, it's like that if you change those settings. So that I would think of an experimental thing that I'm happy if people try it, but do expect a couple of rough things.
Rough edges, yeah, for sure. And actually, so I have a question related to that. But first, Eliot, do you want to add anything about this presentation of the different method of mass matrix adaptations?
Yeah, well, I was gonna add anecdotally, like I pretty recently had a GP model that took like an hour to sample with diagonal, and then changing it to low rank, it was like a matter of seconds. Like the speed up was crazy. So
wow,
I would definitely like, if it's definitely worth trying out. Especially for I think models where you have some reason to think that you might have like a very correlated posterior for some reason, either due to like constraints or I didn't go under the hood and really figure out why it was making that GP model so much quicker, but I think it could have something to do with that. It was a GP2. Maybe it works particularly well for those. I'm not sure. But yeah, so I would encourage people to try that out if they're if it's taking a long time with the diagonal. It could give you an insane speed up.
Yeah. So you mean going from the default diagonal adaptation to the low rank plus diagonal one, right? Interesting. Was it a vanilla GP or a GP approximation like HSGP or something else?
Actually, don't remember. It might have been vanilla.
Yeah. Okay. Yeah. That's my intuition too. Like in my experience, it's gonna it's going to help with vanilla GP. But if you're using an approximation already like HSGP, which was my case actually for the model I mentioned earlier, it's not helping much because the adaptation, like the diagonal adaptation, is already working well because the model, like the geometry is much easier because thanks to HSGP, it's much more of an almost linear problem. And so that makes for a much easier geometry, which leads to actually my follow-up question on that. Maybe for Adrian first and then Eliot. It's okay, so we have these different ways of doing the adaptations. But the issue is that, and I guess it's going to be for most users, like not for you because you have an intuition, and once you start working on these models, you get an intuition of what's going to work best. But my question is, well, if I only know what the best adaptation is once I've sampled my posterior model, it's not that useful, right? And that makes the iteration much longer than it needs to. So is there a way, and even is there research and something you guys maybe are working on, which would be like ideally for the users, I'm thinking, well, we do that adaptation ourselves, under the hood, and we're able to more or less understand what the posterior geometry is going to look like. And then we just, under the hood, Nutpie is like, oh, here I'm going to use low rank plus diagonal because it's going to work better without even the user knowing it, instead of doing it manually and incrementally. So yeah, is that something possible? And what would you tell people right now to do it?
So I would say it's a good question for sure. Kind of this idea of users just trying lots and lots of different sampler configurations is not something I'm actually too happy about. So kind of this Stan way of, here is the sampler, write the model. If it doesn't work, fix your model. I think that's, in many ways, that's the right way to think about if you're building statistical models and working with them. If you start playing with the sampler and spending lots and lots of time of playing with the sampler, at some point it's just much better to fix the model. Just fix the model, and the sampler will not be the problem anymore. As a developer, that's of course different, because I want to kind of increase the size of things that work out of the box, right? So there's a bit of a
same.
Yeah. So automatically choosing, I think that's what we want. And in a sense, that's what the low rank version already does. So it will kind of compute the full, or not the full, it will compute a mass matrix with a larger number of eigenvalues, and then throw away those that look like they are too small to do anything useful. So it only keeps those eigenvalues that look like they do useful work, and it gets rid of the other ones.
Okay. Yeah.
So there's still the additional cost of figuring out what would have been the options, right? There's also the cost of, that there's this additional cost, so we don't want to do it every step. For instance, kind of the diagonal mass matrix we update in every draw. The low rank one we don't update in every draw because that takes time. So there is a trade-off, and I don't know a way of getting rid of it entirely. But as I said, we are trying to kind of make the low rank version kind of the thing that chooses automatically. But how well we are there, that's
Yeah. No, I understand. But yeah, that'd be great. So, and it sounds like at some point you're going to make the low rank adaptation the default in Nutpie once you're happy with what you're working on right now.
That might happen, yeah. I don't want to kind of say that, promise that in any way, but I think that might happen.
Okay. Eliot, anything you want to add?
I would add, I guess I think for, at least in my experience, I think Adrian would agree, like for any sampler, you can always conceive of a posterior that will totally thwart it.
Yeah.
You can always have either like tail behavior that has some totally different covariance structure for some reason or whatever. There's also just the classic, there could be a mode a million miles away that you'll never find. So I think it's a matter of, as Adrian said before, of what works on average better.
Mhm. Yeah. Yeah.
And then, yeah, I would add to what Adrian, I feel the same way in that there's sort of an interesting kind of tension between, like, you want, the software to be as user friendly as possible, and but you also don't want, if some posterior is really horrible and the user just presses go, and you'd sort of like there to be some feedback that, okay, we can sample this, but you should know that we had to whip out this normalizing flow to do it. So you should also maybe consider, reparameterizing or something. I know also there's some work on automatic, like, reparameterization before, like, even pre, not in the sense of how we've been talking about it, but pre-sampling, via a PyTensor or something. If they see some pattern in a model to just rewrite it, which I don't know too much about, but I believe that's going on, which would help too.
Yeah. Mm-hmm. Yeah. That definitely is going on. I don't know if you're working on any of that, Adrian. If you are, we can touch on that topic a bit later in the recording. But I think actually it's a good time to also talk a bit about the benchmarking that you're doing in the paper, because you're actually doing exactly that kind of benchmarking with the low rank plus diagonal mass matrix adaptation in the paper, where you're comparing a lot of models, like if I remember correctly, more than 100 models, and you're showing that the low rank plus diagonal approach outperforms the industry standard by a big factor. Don't remember the exact one, but it's big.
The median difference is like a factor of 4, so it's
right. Yeah,
sometimes it's huge. much more than 4, but
yeah. So were you surprised by how big the gap was, and do you have any idea of why that adaptation works so much better? And also, well, addendum to that question is, you were saying that this adaptation is more or less the case where Nutpie is trying to automatically guess the difficulty of the posterior. So I'm guessing this is related to that. But yeah, like, can you explain also the intuition behind why you're saying that?
Yeah. So what the low rank one does fix that the diagonal one doesn't fix is correlations. So static correlations. So you can have correlations that change depending on some other parameter. It will not fix that. It will also not fix funnels or whatever other kind of weird, crazy geometry you have. But if you have correlated posteriors, it can fix those. Up to a point, there's also kind of, especially if you have a very, very large model with lots and lots of parameters, then kind of estimating what the correlation is gets harder and harder. So it will start fixing things less. But still, correlations just are very common in models. We know that for various reasons. For instance, if you have hierarchical linear regressions and you use centered parameterizations, which is kind of usually what I write down first, and you have lots of data, you end up with strong correlations. If you use non-centered parameterizations, then you often end up with very strong correlations. Or if you have over-parameterizations, you end up with often very strong correlations. So there are lots of reasons why many models will have large constant correlations in them, and fixing those, it makes sense that fixing those helps a lot. So in that regard, it's not surprising. Then the question is kind of how common is that actually in models? And that kind of gets back to kind of how difficult it is to actually benchmark samplers, because kind of if you look at papers, it's quite common that papers will cite, here are 5 models. I tried it on those 5 models and hey, it works. Yeah. Yay. But I mean, you don't even need to be maliciously cherry picking for that to be a problem, because I mean, maybe you developed your sampler with those problems in mind and you chose your hyperparameters such as works there. that happens incredibly easily. So you need more models to really evaluate it, but where do you get them? Where do you get kind of what field? Different fields use completely different models, have completely different typical posteriors. What do you use there? So the best set of models that we have is posterior DB, I would say, and it has big gaps. It doesn't have that many really big models. It has kind of lots and lots of relatively small models that are sometimes very easy, sometimes very hard. And it also has larger models. It's not like there are none in there, but you all still need, I mean, it's a bigger benchmark, I would say, than most other papers have, but you still need to take it with a grain of salt because like your models might be different than the models that happen to be in posterior DB. But in general, I would say, yes, it makes sense that the low rank version works better in many actual models.
Mm-hmm. Yeah, I think that's really a takeaway for most of the listeners here, right? It's like, first, honestly, if you're using PyMC models, just use the Nutpie sampler, honestly, by default. That's what I do in my own workflow, and you're gonna get, like, even out of the box, you're gonna get a really sizable speed up on CPU, and then if you're using GPU, even more. And you have all these different mass matrix adaptations, and then, well, definitely try the diagonal plus low rank mass matrix adaptation. I would say even like almost out of the box. I'll definitely do that now. Each time I have Nutpie on my environment. So yeah, it's a great takeaway. Eliot, I know you worked on that too, so I'm guessing you have very interesting thoughts also about what we just talked about.
Yeah, I think I would also add that I believe posterior DB is open. So if you have a model that isn't running well and or is sampling well, I think you can always add it to posterior DB. And I think there's a lot of more models. It would be great to have more models in there to reflect like the diversity of models that are being used in different fields and whatnot. So I think that's very much like a an ongoing thing. I think there's also one in Blackjacks. They have Inference Gym as well, which I think has some very different models from what if I remember correctly. Yeah, and I know there are some people working on building those up so that they reflect kind of equivalent to what they have in machine learning with all of these huge benchmark data sets. Be great to keep adding new posteriors in.
Mm-hmm. Yeah, and actually, we haven't talked about posterior DB mostly on the show, so I think a lot of listeners don't know what we're talking about. So can you actually define what this is, Eliot? And
so it's basically just a repository with a couple of like 120 or something like that, mostly Stan models.
Yeah. Okay.
I think a couple of them are ported to PyMC, more are ported in a pull request somewhere, but it's most of the models, as I said, are in Stan with the corresponding data sets, so you can kind of mix those up and run those. So nothing particularly fancy, but really, really valuable.
Yeah, it's a great effort to try and benchmark the models, basically. Not the models, the samplers. And as you were saying, it's a very complicated job to make an apples to apples comparison. And basically, this effort is trying to make that right, to do that right. And actually, I'll put a link to posterior DB in the show notes. I think it's interesting for listeners. And well, Adrian and Eliot, you both mentioned about that low rank plus diagonal approach. So it works incredibly well in a lot of cases, but also on some problems, it doesn't work at all. And it can fail spectacularly, but you don't have a clear idea and understanding of why right now. But what are your hypotheses? What are you thinking the problems might be? Eliot, maybe you can start, and then Adrian.
Sure. I think, you know, as I said before, like it's always going to be an issue of averages. And so sometimes for specific models, you're always initializing somewhere that can be completely arbitrary. And, once you're off on the wrong track, things could just get worse and worse. And so some, like unholy combination of adaptation mode, local geometry, initialization points, and posterior. That would be my hunch. I think probably like it. I don't know if it's something systematic or just it would require like an inspection on a model to model basis. But yeah, I'm not really sure. What do you think, Adrian?
Yeah, so about it failed spectacularly. It's been a while that I've seen one where I would kind of use where I would say it like that. So we definitely had some in the past where there were just some overflows, or you could somehow smuggle a none through the tests, some kind of through the cracks somewhere, and you ended up with a none, and then everything failed. But things where it works less, or kind of just maybe kind of you change from diagonal to low rank, and suddenly your tuning isn't long enough anymore, and something didn't actually converge, so you'll get horrible results or something like that. That definitely does happen, and I think that'll just, to be entirely honest, I mean, we can fix individual things and hopefully get more of them right, but there'll always be something that's
right. Yeah. No, for sure. Yeah. As Eliot was saying, it's a matter of averages, and I mean not even only averages, but mostly distribution of cases, right? If you're able to cover the bulk of the distribution of cases, that's the goal of Nutpie, right? It's not a customized package for just one kind of model, so you cannot really zero in on these kind of issues. Something actually.
Also yeah. One thing I've noticed quite a lot as well is kind of if people compare Nutpie and Stan, or Nutpie and other samplers, that it's relatively common that people kind of try to compare cases where both samplers haven't really converged well. So where the effective sample size is actually still 4 in some cases for one parameter or something like that. And I think that's an important thing, kind of, how do you compare that? Because, I mean, it can still be meaningful, right? One sampler might get much, much closer to the actual posterior than the other one. But if you don't know what the actual posterior is, it's really hard to tell which one it is. So,
yeah.
So if you compare samplers, be careful, really, really careful if none of them have converged yet. Converged in the sense of decent effective sample size for all parameters, not just all but one parameters or something, but all parameters, no divergences and so on. If you have that, then you can compare the samplers. If you don't have that, it's still interesting which sample does better, but it gets much, much harder to figure that out. And to the point of right now, I don't know how to do that. So in the benchmarks, for instance, we just excluded everything where none of the samplers converged. We just threw those cases out because they are important, but I don't know what to do with them. So I think that's also an interesting thing to keep in mind.
Yeah, definitely. Okay, so it's like when you're comparing samplers, you have to be even more careful of having all the green lights, right? Because when you're working on a model for a project, you don't have to have all the green lights as long as the parameters that are the most important for your study are having the green lights. And if you have some orange lights for some nuisance parameters, that's fine. But if you're comparing the samplers, you really, really want to be in the best of cases. And Eliot, actually, I'm curious if you know about that, and Adrian also for you. The intuition I got about the diagonal plus low rank adaptation is you do need a bit more time in tuning, right? For it to be efficient. Or is that the wrong intuition?
I think that's right, because you need an eigen decomposition, which is O of n cubed, if I'm not, that's right, I think. Yeah, so there's a little bit of additional like work, I think. But I mean, I think it pays off really well, as evidenced in
sure. In the paper. Yeah, for sure. Yeah. The idea here being like kind of amortizing the sampling time with a bit longer tuning time, which in a lot of cases definitely pays off. It's like, it's like
Just
eating healthier
in there
than you're
real quick. It's not
gonna live longer.
So if we're talking about kind of the performance of the low rank one, that's not n cubed. So that's a little bit better because of the low rank structure that we can make use of.
Yes. Yeah,
so if you do an eigenvalue decomposition of a full mass matrix, that's n cubed, or the dimensionality of the problem cubed. The low rank one is better than that, but it still costs something. So
yeah, for sure. Okay, yeah, but thanks. Good precision. Thanks, Adrian. And so I'm like to zoom out a little, starting to play us out here because, starting to get late for you, Adrian. So I want to be mindful of your time, but where would you say your paper and just the research we just talked about, where does it fit in the bigger picture of Hamiltonian Monte Carlo research right now? And are there other adaptations or preconditioning ideas that you're watching closely and you think have a lot of potential?
So in general, I think there are lots of ideas floating around that are interesting. I'm not sure if we have time to list them all, because there are many, many really cool things around, I would say. But on the preconditioning one, I would say there's not that much. I don't want to, maybe I'm missing something important. But so there was a paper that's definitely important. I should add that looked like at something that's a bit similar to the Nutpie mass matrix, but just using the scores instead of scores and draws. But in general, I would say it feels to me like we kind of have kind of the state of the art there right now. I would say. Maybe somebody else disagrees, and I don't want to kind of mess that up in any way. But on other parts of sampling, I think there are lots and lots of really interesting things happening. There's the sparse nuts, for instance, that was going on in Standos Discord. There was a bit of a discussion about that a while ago, for instance. That's more about the idea of using more information about the model. So right now, most samplers that are used are really black, kind of Stan and PyMC at least, are really black box samplers. So they take the log P function and nothing, like log P function and its gradient and nothing else. But there's lots more information in the model in a sense, and it would be really, really useful to use that for preconditioning, for sampling, for all manner of ways. So I think that's a really big topic for sampling in general. Then kind of on the HMC side, there's, for instance, MCLMC, kind of the microcanonical sampler. I think that's really cool. I'm not entirely sure how much better it actually is. I can definitely come up with an example where it's better. That's really interesting line of work, I would say. Then there's walnuts, for instance, kind of the idea of choosing step sizes dynamically, because kind of in HMC, as we are implemented right now, we're always using constant step sizes. And in some ways, that's just dumb. We just shouldn't. We just should say, okay, here we need small step sizes and here we need large step sizes, which every ODE solver will do. But that's hard to do while still keeping the posterior exact. And walnuts is a way of doing that. I think that's really cool. Also, I recently came across a boomerang sampler, which is also kind of the zigzag sampler, kind of that family of things, if you've heard that. That also has an HMC-like variant, for instance, and I've been thinking that could also be a dynamic step size HMC in a sense, so that's cool as well. Then there's the whole line of work of using GPUs better, so kind of having many chains instead of only few. Yeah, so I'm forgetting things, but the general gist, I would say, is of things I've been thinking about, of other people's work I've been thinking about, but lots of cool things.
Yeah, that's great. Thanks for this list, Adrian. I definitely need to put a link to Walnuts in the show notes, so I'll do that later for sure. And by the way, for those of you looking on YouTube, it's amazing now because of sunset. Adrian looks like a black shadow. It's amazing because you look like you're, one of these anonymous testimonies in documentaries. So I'm gonna make sure to anonymize your voice for that part of the episode where like you're giving us the dark secrets of the HMC world.
All clouds all day except for right now, so that's
oh damn. Yeah, Elliot, anything you wanna add on that, like ideas that you're paying attention to in the adaptation and preconditioning world?
Yeah, I mean, I not so much adaptation and preconditioning. I know that diffusion models are like all the rave right now, and I think there's a lot of people working on how to use those to precondition densities. I personally don't know much about those, nor I'm also not sure if there are actual like software project, open source projects for wide use, with those implemented. Yeah, I guess broadly what I'm most interested in moving forward is different ways of parallelizing MCMC, I think, and making it, scalable to ultra high dimensions, because MCMC is inherently like a very sequential algorithm. Meanwhile, a lot of the, computational advances that we're getting in hardware are for parallel computation. So I think that's kind of an interesting. There's some interesting ideas on how to bridge that gap, but I would agree that for preconditioning, yeah, it seems like Nutpie is state of the art.
Yeah. Yeah, I was gonna ask you actually, what are you gonna focus on in the coming month? Things you wanna learn in particular or explore?
Yeah, I particularly interested in a new way of parallelizing MCMC over like trajectory length. So there's so there's a method of you basically can solve an optimization problem to solve a full MCMC trajectory. Instead of computing in sequence, you can make an initial guess for a whole trajectory and then iterate on it, and it provably will converge to the true trajectory, which I think could be really cool for problems where the chain actually is somewhat predictable to some extent, but the log p evaluations are really expensive, for instance. I think it doesn't really work. I mean, part of what I'm interested in is how that can be done for adaptive samplers where it becomes a little more complicated. So that's one thing I'll be focusing on a little bit.
Yeah. Sounds like fun. And Adrian, what about you? Because you always do some fun stuff, investigating some new ways of doing things. So yeah, like I'm curious, what's on your mind for the coming month?
Yeah, as always, I've got more projects running than I can actually finish, or I don't know. So that's always a little bit of a problem, kind of focusing on particular things that I can actually get done. But as I mentioned, MC LMC and kind of the non-adjusting methods. That's something I've been looking into.
Mm-hmm.
So for some reason, I haven't really gotten it to work as well as I wanted to. So I'm not sure how much. So maybe it's entirely possible I'm just doing something wrong, of course. So I don't want to bash on the methods at all in any way. But so far, I didn't have too much luck, but that could be me. So it's a question of how much I want to try that more. Definitely, I'm looking into kind of what I mentioned a little bit in the beginning is of kind of using higher order autodiff as well. So not just the Fisher divergence, but what happens if we also use second order derivatives. I think there's really cool theory that could tell us how to do that. So that could be really, really useful or interesting. No clue if it's actually will turn out to be useful, but fun for sure. And then probably looking more into walnuts and this boomerang sampler idea that I mentioned. Kind of two completely different things, but both I think can be thought of as the walnuts for sure, but the boomerang as well, kind of an adaptive step size thing, which I think could really help a lot, because I think cases where that would be really useful are quite common. And kind of this idea of using more model information, that's also something I really, really like. I've been looking into that a little bit with Ricardo, where we now have a little implementation that can choose between centered and non-centered parameterizations automatically, for instance. Moves that into the mass matrix adaptation, which I really like. But there are many more ideas in them.
Yeah. Mm-hmm. Yeah, I think that last one actually is a very fun one. I saw it this morning in the Discord of PyMC. So maybe can you expand a bit on that? I mean, it's something we've already mentioned on the show with you and other guests, but that's great to actually see an implementation of it that seems to be working. So yeah, can you tell us a bit more about that and if people can already try it?
Yeah, so centered, non-centered parameterizations are one of those things that if you've seen them once, kind of it's relatively easy to understand how to do that. So you take a normal distribution, you either say it's sigma equals it's kind of some standard deviation that you want, or you set sigma to 1 and then you scale the normal variable up with your standard deviation. And it's the exact same thing. It doesn't make a difference kind of meaning-wise. It's boring. But it can really, really influence sampler performance. So if you do it wrong, and wrong means depends on your data set, right? It's not like wrong, you need to always use non-centered or something, but sometimes you need to use centered, sometimes you need to use non-centered. Basically, if you have lots of information, you want to use centered, so lots of data for that particular parameter, and otherwise you wouldn't want to use non-centered. So that's a mess. That's no fun at all. But turns out kind of this general framework that Nutpie uses to learn transformations, we can use that to choose that automatically. And not just the extremes of centered or non-centered, but there's a parametric family in between. You can say halfway non-centered and halfway centered, or 3/4, whatever. And that's one parameter that you can just think of as a parameter for your parameterization. A transformation parameter. And you can basically treat that as part of a normalizing flow if you want. A really, really cheap one, really one that's easy to evaluate. So much nicer in many ways than kind of the big neural networks or something. And you can just learn it during sampling. So the implementation that we have, it's still in the PR, it's a draft, it's not done yet. It works, but it's not deployed in any meaningful way. It just looks at a PyMC model, looks at normal distributions that have standard deviations that are random parameters, and adds kind of parameterization parameters in a sense that say, do we want to have this as a centered or non-centered one? And then we add that in the mass matrix adaptation and just learn, well, where should we place the dial? And automatically choose that.
Yeah, this is awesome, because basically the idea would be, well, the user writes whatever model they want. Usually they will write the centered parameterization because it's much easier to code and write and understand for humans. But then once you kick off sampling, PyMC would give that to Nutpie, and then Nutpie under the hood during the mass matrix adaptation would be doing that reparameterization between centered and uncentered, which would be like a small normalizing flow adaptation. So adding a bit of a cost in tuning time, of course, but then really rewarding you for sampling time, and also just making the model much easier to write and sample from.
Yeah. Also, kind of, if you do it manually, often you need to resample, right? So I'm not sure kind of saying it's taking sampling time is actually true, because kind of it's just sampling time you now don't need to spend changing your model. And
completely. And you're trying, and you're also getting a better scenario where most of the cases, I'm guessing, are going to fall in between the pure centered or pure non-centered. Just
I don't know yet, but that's an interesting question. I'm actually curious how that turns out.
Yeah, exactly. I mean, I guess from a prior perspective, I think it's easier to bet on the fact that the distribution is probably more like inverse U-shape instead of U-shaped. But yeah, that'd be my bet. But I'll be happy to hear if I'm wrong. And most of the cases are like pure centered or pure non-centered. Also, something that's useful, I don't know if you have that already in the implementation, but it's the idea that you don't have also to have fully centered for the whole model or fully non-centered for the whole model, where it would be like some clusters would be maybe fully centered, some others would be fully non-centered, some others would be in the middle. Would that be working like that already?
Yeah, it's doing that. It's doing that already. So it's kind of on a per variable basis. Not even per variable, but finer grained. So if you have one big normal distribution with some crazy big shape, then it can learn that, okay, some of those individual normal distributions kind of inside the big normal should be centered and some should be uncentered, non-centered.
Yeah, okay. Yeah, which is awesome. Which is basically like the case you want, where you're able to infer the whole continuous space of that spectrum instead of artificially reducing it to a binary choice, which is what we're doing right now, but just because of the technology limitation, or maybe just like time limitation. Whereas like if you're modeling,
I've actually used some versions in between. It's not too hard to do kind of manually either. It's just a pain. So I don't think nobody does it because of that.
Yeah, because it's just like so many cases to try. So I think it's a perfect use case for automatization for sure. Awesome. Wow, that's super cool. Eliot, anything you want to add on that before I ask you the last two questions?
Well, let's go ahead.
Okay, awesome. Well, Adrian, you've had already these last two questions, so if you want, like, you can answer them again, actually. But Eliot, it's your first time, so first one is, if you had unlimited time and resources, which problem would you try to solve?
Like any...
And careful, it's a trick question, because it doesn't mean just in Bayesian stats. He got me with that last time.
Yeah,
okay. Well, I would say maybe something, which problem? Maybe like the clean energy problem. Like, how do we, convert to 100% clean energy? That'd be cool. I'd probably work on that.
Okay. So I guess the closest to that would be fusion, something like nuclear fusion now, or something like that. Okay. Yeah. Well, that sounds very interesting and important. So I love that. Adrian, you wanna change your answer from last time? Maybe you solved already your first problem, so you want another one.
So the sampler is now actually a solved problem. Okay, that's nice to hear.
Yeah, exactly.
Yeah, I guess somehow fixing the democracy issues that we are facing, but I'm not sure how infinite resources would help with that. Seems more that some people have infinite resources seems to be more part of the problem. I don't know.
It's gonna take longer than a few episodes, so I guess when you come back, you won't have to answer this question again. And second question, Eliot, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Maybe does can I say like Kurt Gödel? I mean, he's not really a scientist, I guess, mathematician. I think that would be my especially since a lot of the work he did was when he was like 22 years old or something. So I think very young. I would say him.
Yeah, I mean, great choice, and you're the first one to answer that. So well done.
Nice.
Adrian, you wanna maybe have another dinner with somebody else?
Another dinner. I'm actually not sure who I chose last time.
Yeah, me neither. But we can go back to your transcript and check.
I guess it probably was Bertrand Russell, so I'm not gonna choose him this time.
That's possible.
Maybe let's pick Euclid, for instance. That sounds like fun. If we assume that language barriers are not part of the thing there, but because otherwise that would be a very, very boring dinner.
Okay, so I will check who you chose, but actually, you know what? I think you picked Euclid. Now that you yeah, I remember you saying something about language barrier or something like. Yeah, we'll see. But I mean, if you did pick Euclid and then did that again independently, it means like it's really a revealed preference. So we definitely need that dinner to happen. Hopefully next time you will have had it.
Yeah.
Awesome.
Time Machine is almost done, but still kind of the last 10%. It's always the last little bit. So the seed is
exactly.
there.
Yeah. It's the Time Machine
engine that's missing some tiny piece.
Yeah. Time travel is really an endeavor where the Pareto effect really doesn't kick in. It's just like 80% of the result doesn't get you there. And actually, nobody answered time travel for the first question in the history of the show. So I am surprised actually now that we talk about it. Maybe it's not that important. That may be why. So it's only important to me. Awesome. Well, guys, thank you so much for taking the time. It was a pleasure, Adrian. Always a pleasure to have you on the show. Come back anytime. Eliot, really great to have you for the first time on the show. Hope you enjoyed it. And also, you're welcome anytime. Thank you to Bob Carpenter also for working with you guys on this paper and all these topics. I know he's doing an amazing job at the Flatiron Institute and the whole team. So, as usual, there will be a lot of links in the show notes. Feel free, guys, to add any links to papers or tutorials or things like that you think are worth sharing. And thank you again for taking the time and being on this show.
Thanks so much. It's been a blast.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbayesstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.